Hello and welcome to tutorial number 3 of this overview series of tutorials that cover the GNSS software radio toolbox for MATLAB. So in the previous tutorial we were talking about the state machine controllers. So let's pick up where we left off and talk about this CA code control state matrix. So as we were talking about last time, each of these rows describes a tracking loop state and also describes the transition between one state to another. Okay, so now let's go down one by one in rows and see what's going on here in this matrix. So the first row is saying it's a type 1, which means load the acquisition parameters, and K means run those parameters, load and run them for 500 milliseconds, and these two mean use the pre-detection integration and post-detection integration values from the acquisition process. Again, the reason you want to do that is the acquisition process that found or successfully acquired that signal may have had to use a certain combination of pre-detection integration and post-detection, or rather coherent and non-coherent integrations to have the acquisition be above a certain threshold, the signal to noise ratio be a certain threshold in order to successfully acquire. So when you now want to pull that signal in to be tracked, you want to run the tracking loop with the same pre-detection and post-detection integrations. So by the way, if this is not obvious, pre-detection integration is the integration time that you use to run the carrier tracking loop. So you basically integrate for, like over here, 2 milliseconds and dump the correlators, and then you form the carrier frequency or phase discriminator outputs that then get filtered and applied back to the carrier replica NCOs. ADI, which I call after detection integration to set it apart from pre-detection, is the number of pre-detection integrations that you combine non-coherently or coherently, as the case may be, in order to run the code tracking loop. So over here, for example, we have a pre-detection integration of 20 and a post-detection integration of 10, which means you multiply these two and the effective dwell time for the code tracking loop discriminator updates is 200 milliseconds. Okay, and keep that update rate in mind, because when we set our loop bandwidths, we have to make sure that the Nyquist criteria is satisfied. In other words, you have to have enough update rate that is at least twice that of the bandwidth, the loop noise bandwidth that you have set for your frequency lock loop, phase lock loop, or delay lock loop. And typically, as a rule of thumb, you want to have at least 3 complete cycles represented in your duration to give it adequate time for that tracking loop, the new parameters to settle down before you transition over to another state. If you fail to have enough um, dwell time for the state such that the loop hasn't fully settled down, it's possible that you could lose lock when you go to another state because you're kind of shocking the tracking loop before it has a chance to settle down. All right, so let me continue to explain this here. So in this state, we are using a carrier loop order of 2 and a FLL bandwidth of 10 Hertz. And the reason for such a relatively high number is because we are going to pull the rough Doppler frequency offsets, pull that into a more accurate value, and we want to do that fairly quickly. So that's why the bandwidth is set to 10 Hertz. The PLL bandwidth is 0, as I mentioned in the previous tutorial, because in the beginning we want to run a FLL because that's the most robust tracking loop there is, and especially in the midst of data bits, because in CA code you're going to have data bit transitions, and having a FLL allows you to track robustly in the midst of those data bits because we have not achieved bit synchronization yet. We use mode number 1 for the frequency discriminator, mode number 1, which is Costas loop, for the phase discriminator, even though it's not enabled over here. The code tracking loop order is first order, and similarly for the code tracking loop we are using a bandwidth of 10 Hertz. And again, the reason for this is during acquisition you don't have the exact code phase, and so the goal here is to pull the code phase in as quickly as possible. So that's a 10 Hertz bandwidth for that. We are doing carrier aiding of the code loop all throughout this state machine, and the early minus late correlator spacing is 1 chip. So again, this is for robust pull-in of the code tracking loop. The DLL discriminator identifier is 3, which means this is a envelope early minus late divided by prompt discriminator implementation. The user mode is 0 because there's no special correlator output combining implemented in this matrix for CA code. The next states are all set to nans, which means this matrix is just going to go simply from this state to this state and on down. Alright, and then the PLL threshold, I usually set that to a value that is above 1 to disable it. So this is the threshold that's used in the phase lock indicator, and the phase lock indicator is a implementation that goes between +1 and -1. So +1 means you're phase locked, -1 means you're phase locked to the opposite phase, which means if you're supposed to be locked on the I, then -1 means you're locked on the Q, and 0 means you're not phase locked at all. And so we'll see what that looks like in the simulation. Um, and here, so basically having set to 2 means that we are not using that mode for transition in this state. And then the measurement is not reset in the first state. So what's going to happen is in the first state it will run pull in for half a second and then transition to this state over here. And this state mode is the code carrier divergence check and correct mode. So this k parameter is telling you the dwell time for that code carrier divergence check. So here it's set to -1000, which means this algorithm is going to measure code carrier divergence over an interval of 1 second. And -1000 means that it's going to actually perform the correction. If you didn't have a minus, it's going to just report what the correction should be, but it will not apply it. So we want it to be applied, and so we set it to -1000. Now, assuming that the carrier tracking loop and the code tracking loop settle down within that half-second interval, it's best to do this code carrier divergence by coasting. And so in order to coast, we set specifically coasting the carrier tracking loop. So in order to coast, we set the FLL and PLL bandwidth to 0. And so as a result, it will coast on those initial pull-in values. And if there's a divergence, it will correct for that. The reason it's good to do coasting, especially for signals like CA code, is that because there's no bit synchronization applied yet, the coasting helps it to track without being influenced by the bits that are changing, because synchronization is not achieved. Alright, so all the rest of the parameters are as above. In the third state, so this is something that is implementation specific to this matrix. So anytime you have a code carrier divergence check, you want to have a dummy state where these two parameters are set to 0 in order for that code carrier correction to stick. Because what happens is if you set an FLL bandwidth here, even though the correction is applied, the FLL bandwidth, the frequency lock loop tends to pull that out. Okay, so you want to have this dummy state where it's set to 0 and 0 for FLL and PLL bandwidth, and you can do that just for like 10 milliseconds, and that should be enough to allow that correction to stick into the NCOs. Actually, it's the velocity integrator that is corrected as a result of this code carrier divergence. Which also means that in order for this code carrier divergence to work, you should have at least a second order carrier loop filter implemented. Okay, so this code carrier divergence correction will not work if this is set as a first order loop. Alright, in the next state number 4, what we do is bit synchronization. So state type number 2, and here the k parameter refers to the number of bit transitions to use in order to build a histogram of transition skews in order to find the skew between um, the current integration epoch and the integration epochs that are in the signal. So the histogram is built using 20 transitions. And while this bit synchronization is running, we run the loop at 5 Hz FLL and 18 Hz PLL. So it's already, the idea here is to now run it as a FLL aided PLL to allow it to approach PLL mode. And the rest of the parameters are the same except for the bandwidth of the DLL, and that's reduced to 5 Hz because the assumption is that now the code tracking loop has settled down and we can now start to decrease its loop noise bandwidth. Alright, so now in the fifth state, we are doing a transition based on the phase lock indicator. So in order to disable it transitioning to based on time, we set this value to -500. And so what -500 does is that it will first run this as a timed loop for 500 milliseconds, and that's actually, this 500 is the timeout value. And after the timeout, it waits to transition based on the transition condition. And in this case, the transition condition is only one in this toolbox version, and the condition is that the phase lock indicator reaches a value that's above 0.9. And so the idea here is that you're running this as a FLL aided PLL, which means it's going to try to become a phase lock mode, but there is robustness built in because of the FLL. And at some point, that phasor is going to reach PLL mode tracking or phase lock. And when that happens, the indicator will go to somewhere near 1, and as a result, this will trigger the transition to this state. And in this state, state number 6, we are basically doing a time transition, and here we turn off the FLL. So the idea is that now in the 6th state, we are on a complete PLL with no FLL aiding. And as a result, we also turn off the FLL discriminator over here. So by this time, we are assuming that the code tracking loop has achieved full steady state tracking, and so as a result, we can now start to change the correlator spacing. And in this case, we are going from 1 chip to 0.5 chips. And here, this is another caveat. So once you have done one of these phase lock indicator based transitions, it's always a good idea to set that back to a value that never triggers that state. Alright, so moving on, now that we have full steady state PLL Costas loop tracking, in the next state we set the tracking loop order to 3rd order. And so this will allow us to track acceleration dynamics. In the same state, we now can set the delay lock loop bandwidth to 1 Hz. So the idea is to, keep dialing that down in order to give good code measurements. And we also, now that we have reached phase lock tracking for the carrier, we can change the code loop discriminator to a coherent loop, which is what number 8 does. Okay, in the next state, we change the coherent early minus late into a coherent HRC double delta implementation. Okay, and then in the next state, we start to now change the integration times. So here now, all this time we ran whatever the acquisition process gave us, and then over here we go to a 2 millisecond pre-detection and one the same 2 milliseconds post-detection, and over here now we go to 5 milliseconds pre-detection, and in the next state we now go to 10 milliseconds pre-detection, and at the same time we bounce the spacing up to 0.25 chips. In the next state we go to 20 millisecond integration, and in the next state we now go to 20 millisecond integration with 10 millisecond post detection integration. But actually in this case we are implementing 114, which is a coherent double delta discriminator. So because it's coherent, this ADI is actually not post detection, but it's still pre-detection, and what's happening there is that it's doing data bit wipe off using the 20 millisecond integration output. So it's basically taking the sign of the 20 millisecond output and wiping its own sign out and continuing to integrate for 10 more of those 20 millisecond epochs. So for a total of 200 milliseconds. So essentially what this is saying is that we are running 200 millisecond update rate for the code tracking loop, but because of the 114 over here, it's implementing a coherent delay lock loop discriminator. At the same time here we are changing the spacing to 0.1, and then in the next one to 0.01. Once we have reached this state, because the update rate has been slowed down and also we have come to a very close 0.01 chip tracking correlator spacing, we want to allow some extra time for any deformation of the signal to correct itself, and so as a result we run this state for 2 seconds to allow it to completely get to steady state tracking, and this is specifically for the code tracking loop. So we allow it to run for 2 seconds, and then finally we get to the last state, and here you can see that the k value is set to infinity. So basically what that means is it will never trip a transition on this state, and here everything is the same except for the fact that the measurement reset is enabled. So the idea is we allow everything to settle down here, then we finally transition to this last state where on the onset of that state it will reset the measurements and continue to track for the duration of the end of the run. Okay, so that explains this state transition matrix. In the next tutorial, we will kind of interrupt this process and see what happens to the output of the tracking loop.